Since we've talked a lot about energy, now we want to talk about how that energy changes, or how energy changes in a given setup. So that's going to occur as work, and work occurs when a force is applied over a certain distance. And so the equation that we use for this is work equals the force parallel to the distance that you're pushing times some change in distance. So work is force parallel times a change in distance. So as an example of that, if I'm pushing down like this at some angle, and I'm pushing a box across the floor, I'm only going to count however much of my force is pointed forward, whatever my horizontal component is, because that's the direction that the box actually moves. So I take F, in this case cosine theta, and multiply it by delta x. So that's our equation. And like I said, you need to use the parallel component of force. So find however much force is pointed in the direction that you're moving, and then multiply it by however far you've moved it. So some properties of work. Work is a scalar quantity. It can be positive, it can be negative, but those don't indicate direction. They indicate increase and decrease. The variable that we use for work, like I said, is W, and the units, like with energy, it equals 1 joule, which is also equal to 1 Newton meter, which is also equal to 1 kilogram meter squared per second squared. And if you were wondering, this is how we know that 1 joule is equal to 1 Newton meter. Because if you look at the definition for work, work equals force times distance is sometimes how you see it. The way I had written it earlier was force parallel times delta x. This is going to be measured in newtons. This is going to be measured in meters. This is going to be measured in joules. So we see that 1 joule equals 1 Newton meter. And then if you remember the definition of a Newton, you know that that's 1 kilogram meter per second squared, and you can do some rearranging to get this set here. So as an example, consider a 3 kilogram briefcase. A person lifts this briefcase 0.75 meters vertically. Then they carry it for 10 meters horizontally. Finally, they walk up a ramp for 2 meters. Each segment of the journey, how much work does the person do on the briefcase? Assume each segment that the briefcase is moving at a constant velocity. That matters for something that we'll talk about later, but in this case, we don't need to worry too much about that piece. So if I lift a 3 kilogram briefcase, then what direction am I applying a force? I'm applying a force upward. So my force, that'll be, we'll call that the person force. So P going up, and we have Fg pulling down. And we know those have to be matched because it's moving at a constant velocity. So let me clean that up. So in each case, we'll make the person's force be P, and then we will label other forces accordingly. So there's an Fg pulling down and some force labeled P pulling up. So in that first case, we know that if it's moving at constant speed, P equals Fg. And this is the same in all cases, that P will always equal Fg because the briefcase is moving at constant speed, so the net force has to be 0. So in the first case, and that will equal mg, which will equal 3 kilograms times 9.8 meters per second squared. Sorry, I'm just doing a side, so we'll say P is approximately 30 newtons. And I'm just going to use that for sake of calculations. If you want to use the more precise value of, 29.6, I think, 29.4, you can do that. But for here, we have, again, this being applied. Now, which direction are they moving it? They're moving it 0.75 meters up. So in other words, these are both perfectly parallel. So the work will equal 30 newtons, the force parallel is all of it, times 0.75 meters. And that's going to be equal to 3/4 of 30. A quarter of 30 will be a little bit over, a little less than 8. So 7, so bring it something around 23-ish joules. You can figure that out, but the work is about 23 joules. Technically, you'll more often see work presented as Newton meters, so about 23 Newton meters. That's not really precise, don't quote me on it. You can run the full calculation to do it properly, but it should be roughly there. Now, in the second part, they're carrying it horizontally, but what is our force vertically? So how much of these are parallel to each other? Nothing. So in other words, in the second case, the work equals 0 Newton meters. So it requires no work to move something horizontally at a constant speed. If there's no, if it's a constant force and there's no like resistant force that you're overcoming. So this is why if you push a box, you're going to feel the effort that's required because you're overcoming friction. But if you're carrying something horizontally, you are technically doing no work on that briefcase. Now that's not fully properly true because you're going to have it swinging back and forth, and you're going to have a lot of other things involved that make this more complicated. But in our simple example here, there's no work there. Now, if the person's carrying it up the ramp, that means that our delta x is like this. And so in this case, rather than finding how much of the force is directed diagonally, I'm just going to find what's my change in the direction of my force. So you can do this either way. You can either find the parallel component of the force or the parallel component of displacement. And because in this case it looks like it's easier to just find the parallel component of displacement, I'll do that. So that's going to be delta x times sine of theta, it should be a theta, is equal to my change in x that's parallel to my force. So then if we come back and plug things in, we'll get our 30 newtons of force times the 2 meters times sine theta to find how much of it is perpendicular, sine of 30. And sine of 30 will be 1/2, I think. Unless I make a mistake, I'm going to assume it's 1/2. If it's not, correct me. But that should be about 30 joules. And then that will be our work, or 30 Newton meters, again, more properly. So that's the rough idea of work. If you have questions, let me know, but otherwise we'll give it a pause here.